for coming, everybody. I'm going to talk about some work I've been doing over the last year with a team at Cloudera, integrating Apache Solr with Apache Hadoop. Start off a little history about who I am. Currently work at Cloudera. I'm a Lucene Solr committer on the PMC, an Apache member. I've worked previously, my first job out of college was for a newspaper archiving company, and that's where I was introduced to Lucene. I spent a lot of time replacing an old SQL-based search engine with Lucene. That's kind of where I got started with the community. There was a lot of kind of old features that I had to replicate with Lucene, which led to me digging in to figure out how things work. Soon after became a committer, and then shortly after that joined a company that was starting up called LucidWorks. At the time it was Lucid Imagination, a company that formed to be the commercial entity behind Lucene and Solr. I spent about 4 years there, working pretty heavily on Solr Cloud during that time, a distributed mode of Solr. And then about a year ago I joined Cloudera to help with this Hadoop Solr integration effort. So I imagine everyone here pretty much knows what Lucene is if you're at this conference. Very fast search library, fairly small, really efficient, getting faster all the time, really active community, really awesome code, really awesome tests. It's a pleasure to work on this library. It's very tight, very cool. Solr, Apache Solr, built on top of Lucene, adds a lot of things like faceting, highlighting, distributed search, the new Solr Cloud mode, which is basically like clustering features. You know, everything you would expect out of a search engine that Lucene doesn't really give you out of the box. You normally have to build yourself. You get that with Solr. So in the past, there's kind of a long history with integrating Lucene and Solr with Hadoop at various levels. None of them have really taken off yet. One that was gaining a lot of steam a few years ago that has kind of died out was called Kata. This basically was a index serving engine that basically you know, let you build and serve indexes with Hadoop. I think a lot of the reason it never fully took off was it was missing a lot of the extra search side features that something like Solr has, highlighting, rich text document extraction. Lots of little features that have kind of been added to Solr and polished over the years that are kind of hard to catch up with. Apache Blur, I think, is kind of the successor to the Kata crown. I think it faces some of the same things. It's struggling to catch up with a lot of these extra features, but it is actually does a pretty good integration with MapReduce and HDFS. And for our work, we actually collaborated and borrowed a bunch of code from the Apache Blur project. We've actually contributed code back that we've worked on. So we're not necessarily just trying to replace it. So far, we're kind of living in harmony, even though we're kind of both marching down a similar road. Another integration attempt is something called Solbase, which is an integration of Solr with HBASE. And basically the approach here is to store the index files in HBASE. An attempt that's been made in various other distributed database search engines like Cassandra. Usually you end up having to sacrifice various performance or features, so it hasn't been my favorite approach, but that's something. HBASE 3529. This was an attempt at integrating Lucene with HBASE, another one that never fully took off. Solr 1301, Solr 1045. I believe Andre here was the primary driver behind at least one of those issues. Both of those are basically issues around building indexes with MapReduce so that you can, you know, efficiently in batch build indexes using your Hadoop cluster. That issue has been floating around for a long time. Various people have kind of taken up the torch and pushed it a little bit further each time, but it's never been fully polished and committed. And then, of course, a lot of people have just done various ad hoc integrations, like sending documents from the mapper directly to a Solr cloud server over HTTP, and various other little integrations. So we kind of looked at all this as we were trying to decide exactly how we wanted to bring search to Hadoop. And we didn't really want to start from scratch. So we actually chose Solr 1301 for the MapReduce part to build on. And we also borrowed some code from Apache Blur. So we kind of took what we could rather than starting from scratch. And I'll talk a little bit more about the approach we took with that. But so a little history first, kind of the family tree in the middle there is Doug Cutting. Doug is the original author of Lucene. He started it in 1997. He was predicting the internet bubble burst, he claims, at the time, and was trying to make sure that he had a project to work on if things turned bad. He was a few years ahead, but he took the time to write Lucene as a project to learn Java. Originally, it was closed sourced. He said he had like one customer, and at some point he decided, this isn't really panning out as something to make money, but I'd like to, not just let it rot. I want to let other people use it. So he put it up on SourceForge under the GPL license. Over time, it migrated to Apache Jakarta, and then eventually to its own Apache top-level project. The license changed to Apache 2.0, and over the last decade or so, development and activity on Lucene has really taken off. So in Apache land, there's things known as top-level projects, and these top-level projects often have sub-projects. A lot of reason is it can be difficult to become a top-level project. There's a lot of requirements for it, but it's actually fairly easy to start a sub-project under a top-level project. And so once Doug was kind of done with Lucene and looking for new things, he started something called Apache Nutch, which was an attempt to build like a Google-scale web crawler. He worked on that for a while, and then shortly after he started, I guess Google published their papers on MapReduce and kind of what they were doing to do big data at Google scale. And at the time, they were having trouble scaling Nutch to a large number of nodes, and Doug decided, we actually, I think, need to start a new project that just focuses on the underpinnings of, distributed file system, HDFS, the MapReduce paradigm. And so from Nutch was born this project Hadoop, which has also spawned a ton of its own projects. Most of these projects have spun up into their own top-level projects. They're no longer sub-projects. But it's kind of interesting that they're all kind of children of Lucene, all of these various projects that have now come up, many of them with their own companies behind them. Another sub-project of Lucene, of course, was Apache Solr. A few years back, they actually merged into one project. So the Lucene project is Lucene and Solr, and it's actually one code base, which is kind of simplified a lot of things, at least from the Solr side, in terms of making sure we're always up to date with the latest Lucene code changes. So anyway, the idea basically was, we have all these things. Generally, Hadoop and all of its sub-projects have been fairly separate from Lucene and Solr. Our idea was, okay, how do we bring them together? And so the basic plan was, rather than build something entirely new, let's use Solr, let's use these other projects, and let's just focus on integration points between them and making them play nice together and pushing that all into the upstream projects. Nothing proprietary, nothing that you can only get from Cloudera per se, but let's make these integration points and push them back to the projects where they belong. And then let's focus on just making the integration points really high quality, lots of testing. Lots of work on just making it really nice, lots of documentation, and let's focus on making this stuff really hardened first, and then focus on performance and scale later. And so over the last year, we've been focusing on getting these integration points done and getting it all hardened. So Solr Cloud, this has kind of been my focus for, I don't know, the last 3 or 4 years. This is basically adding clustering to Solr. Solr has had distributed search since about Solr 1.4 many years ago, but it's been up to you to do the sharding and get your data on the various servers. There's been no automatic failover, no automatic recovery. Solr Cloud is basically our code name for a feature set that adds all of these automatic clustering capabilities. So basically, the idea is you can talk to any node in your cluster, add documents to any node, and they will forward those documents to where they belong. If a node goes down, replicas will take over for the node that goes down. When you bring back a replica, it will recover and get all the data that it's missing. So the basic idea is you can search and query and update to your cluster, and as long as a node for a specific shard is up, things are going to keep working. Automatic failover, automatic leader election, and the idea was to make sure it supported near real time. So basically, about a year ago, we released the first version of this in Solr 4.0, and I've been spending, about the last year really working on hardening this. And so this is basically what we wanted to integrate with Hadoop. We didn't really want to do the standard Solr model because, when you think about Hadoop and things at petabyte and terabyte scale, you really need kind of all this automatic failover and clustering. You can't really do an ad hoc, you distribute the updates yourself solution. So that's a big reason why I joined Cloudera. They really wanted my Solr Cloud expertise to help with this integration. So the first integration point that we focused on was integrating Solr with HDFS. And so the basic idea is we want to be able to read and write indexes to HDFS. So why is this? A lot of people ask, well, why not just use the local file system? There's a couple of reasons, none of them, really too much about features and more about cluster maintenance. If you already have a Hadoop cluster, then you're already used to provisioning HDFS at kind of a top-level scale. You're not necessarily worried about how much free space you have on each individual node, but just how much space do you have on your HDFS cluster in general. We didn't want to integrate Solr in a way that said, okay, you're used to, with all of your MapReduce cluster, you're used to just being able to worry about how much HDFS space you have. Now you're also going to have to go and make sure each node has enough space for your indexes and enough space so that when you're merging, you at least have 3 times that space free, et cetera. Wouldn't it be nice if, just like the rest of your Hadoop ecosystem, everything just talked to HDFS and you could forget mostly about the local file system? So people have tried to do this in the past, and generally it hasn't worked out that well for a few reasons. One is just performance. Hadoop is generally not designed to do, or HDFS is not designed to do really well with random reads. Is one of the bigger problems. It likes reading in a straight line, writing in a straight line. It's also an append-only file system. Historically, that was also a problem with Lucene. Lucene did not support append-only file systems for a long time. A few years back, something called flexible indexing was added, where you can write custom codecs that control how index files are written and read. And at some point, someone actually added, I believe that was Andre again, was a driver of this, the append-only codec, which basically let Lucene write directly to HDFS. In Lucene 4.2, that append-only codec actually was merged into the default codec. So from Lucene 4.2 on, you actually had native support to read and write from HDFS as long as you had a pluggable directory implementation that knew how to do it. So basically, this was our first focus. How do we read and write from HDFS? How do we handle the performance issues? And so, yeah, a little bit about what I talked about just now, the append-only file system. But so basically, Lucene, like I said, uses this directory abstraction to read and write files. It's pretty simple. You can create an output file, create an input to read, delete a file, and then there's the make and clear lock for making sure more than one index writer don't mess with a directory at the same time. So it's a fairly simple interface, and basically all you need is an HDFS directory implementation to read and write from HDFS. And that's fairly simple. You basically, instead of using your standard Java file interface, you use the HDFS client interface, and you could actually probably write one of these in like half an hour. It's pretty simple, but you're still going to have some speed issues. So Lucene and Solr really kind of count on the local file system cache to make sure things are fast. It doesn't do a lot of on-heap caching of file system stuff. For sorting and for faceting, it tends to create these on-heap structures for caching. But as far as like actually reading index files, which can be quite large, it really counts on the local file system cache, which you can't always count on with HDFS. So basically, you need some sort of caching mechanism to replace that local file system cache. And the Apache Blur project had already worked on this. They had an HDFS directory implementation that we could just grab rather than implementing ourselves. And on top of that, they had built a block cache implementation that basically caches reads. We actually added write caching support too for better near real-time support. But so we were able to take this and integrate it with Solr. And that basically acts as a replacement for the local file system cache when data is not local. So the nice thing is that normally what you can do is you can run your HDFS nodes co-located with your Solr nodes. And so when those Solr nodes write their index files, they will actually first write a local copy because an HDFS node will be running, and HDFS by default will write a copy locally first, and then if you have a replication factor of 3, it'll write 2 remote copies. So in the standard case, you're not necessarily going to need this block cache. That data is going to be in the local file system cache. But sometimes due to node failover or disk space issues, you may need to go to a remote HDFS node. And this block cache will basically just act as the file system cache and cache data for you, really speed up reads. It can take a little longer to warm because it's reading that data over a network. But once it's warm, it works really fast. So we basically borrowed that from the Apache Blur project. There's been some talk about collaborating on it over time. They've actually rewritten and have a second version of it that we may look at integrating. And like I said, we contributed back a write caching side to this. So basically, with this HDFS directory and with this block cache, that pretty much lets you read and write Solr index files to HDFS with similar performance to local file system. It's a little bit slower in our testing, maybe 10–15%, but it's a hit that's not so bad that you're not going to not be willing to take it. And if you're using upstream Solr, you still do have the option of using the local file system along with our other integration points if you want to. But you can also put the index within HDFS, and over time we're hoping to reduce that small performance penalty. We just haven't focused on that yet. So that put the index into HDFS, but it left kind of a key component still writing to the local file system. That's the new transaction log. We added a transaction log to Solr for Solr Cloud to handle recovery scenarios mainly. It's also good for durability on the single node case. Previously, in the single node case, if like you lost power to your Solr node, you wouldn't end up with a corrupt index because Lucene promises you won't end up with a corrupt index, but you could lose data. We added the transaction log so that if you turn that on, you're not going to lose data. When the node starts back up, it'll replay any data that was accepted from the transaction log and catch you up, basically. So that's one benefit of it, but the main reason that it was written was for recovery in Solr Cloud. When a replica goes down and comes back and it has to recover from the leader, this transaction log is pretty important. And so it was kind of annoying that you still had this writing to the local file system. That still meant that you had to worry about how much space you had free on each of your nodes. So one of the first things I started working on was implementing a new version of this called the HDFS transaction log that basically works the same way. It runs all the same tests, except it simply reads and writes from HDFS. And since it's an append-only transaction log, it was relatively simple. There was a couple little tricky things, but So basically, once that was done, now we've got the index and we've got the transaction log in HDFS. You pretty much no longer have to worry about local file system. Logs are still written to the local file system depending on what logging implementation and configuration you use. But everything else is now in HDFS, which is kind of nice. So all of this has been contributed to Solr. It's been in since like Solr 4.4, and it's pretty simple to use. So to trigger the HDFS directory factory, that's in solrconfig.xml, you can just simply say which class you want to use for your directory implementation. And so you simply say solr.hdfs directory factory, and now you're reading and writing from HDFS. And to get the update log into HDFS, you simply use an update log that starts with HDFS://, and it'll detect that and say, hey, you know, the scheme is, or protocol is HDFS, so I'm going to use the HDFS implementation. And so that's the sample start with the default out-of-the-box Solr config. If you use this command to start Solr, you'll be fully reading and writing from HDFS. So once that was done, that was kind of nice. You've got things working. But there was another big problem, and that is that replication in Solr, which is how Solr will move an index from one Solr instance to another, which in Solr Cloud is used for recovery. Say you add a new replica, it's got to catch up to the other shards. So it will, you know, rather than suck off a few updates at a time, it'll replicate the entire index. And historically in Solr, well, we supported a pluggable directory factory implementation. Replication actually counted on that being a local file system implementation. And there's actually some other spots in the UI, various places that basically assumed a local file system implementation. So I had to go through and basically find all those points and change them to use the directory, the pure directory abstraction, so that you could get replication on HDFS the same way that it works on the local file system. And basically make custom directories a first-class citizen. So it kind of has a side benefit of, in the past, you never really could do kind of crazy out there directory implementations, say one that wrote to JDBC, if you still wanted to use replication and various other features. Now, because we needed it to work for HDFS, you can. If you implement a directory abstraction, then everything in Solr is going to work now, which is pretty nice, because it always annoyed me before that it didn't. So that gave us kind of replication working pretty simply, but there's, and that's how things work currently in Solr in the latest releases. There are some downsides though. You basically get HDFS replicating 3 times and Solr Cloud replicating for how many replicas you have. So it's kind of a, you know, a data explosion. And that's not really ideal because you know, in HDFS, you kind of would prefer that only HDFS did the replication. There's a trade-off you can make. You can tell HDFS, hey, don't do any replication and just store it once and have Solr Cloud do its replication. But the problem is Solr Cloud isn't rack aware as HDFS is. So HDFS will go out of its way to make sure it doesn't place you know, the data for different replicas all on the same rack, because then you lose that rack, you lose all the data. It's actually smart enough to spread it across different racks. And so having HDFS not replicate and have Solr Cloud do it is doable and maybe okay for some people, but it's not super safe. So there's various ways we want to get around this. One of them is simple. If you know how HBASE has region servers and how it handles failover, we're basically going to steal that approach. And the idea is, so if a node goes down, the data that it was serving is not actually on that node, it's in HDFS. So it should be pretty simple to have, like in Solr Cloud, one node in the cluster is elected the overseer. And so the overseer is special and runs some special logic. If it dies, someone else is elected the overseer. So what we'd like to do is have the overseer notice when a node goes down and simply assign the data that it was serving from HDFS to another node that's up. So it's not an instant failover. There's going to be a brief wait as that happens. But you can keep losing nodes, and it can keep saying, OK, whoever's up and is serving the least number of cores, assign that node to serve. And then when nodes come back, it can then spread it. It can say, OK, now move it back to the new node that's up. Create a core there, replicate from the existing core, and then remove the core from the overloaded node. So this is kind of the first strategy we're going to do because it's pretty easy. So hopefully that's going to come pretty soon. I've started doing some of the groundwork for that, and there's still a little more to go. But then beyond that, there's more we want to do. It would be nice if you had the option that actually only the leader of a shard was writing to HDFS, and replicas, instead of also writing to HDFS, they just wrote to like dev null. Any writes that came to them, they do nothing about it. Normally, they might forward it to the leader, but then the leader would send the data back. And when the leader sends the data back, we might still have it do that so that it can populate NRT caches and whatnot. But they wouldn't actually write to HDFS. They would simply read from HDFS whatever the leader was writing. And so then instead of having X copies of the index in HDFS, you just have one copy, and HDFS does the replication for you, and you just have one node in each shard doing the writing. There's some complications around NRT and real-time get that I think are going to be a little hard to solve, which is why this is the second approach we're going to work on. But once you have both options, you'll be able to choose, or still use the original option where you have the data explosion if you want. So it'll basically be 3 different replication options you have. So that's the Solr with HDFS integration story. Doesn't really give you a lot of extras unless you are already using Hadoop and HDFS. You might not necessarily want to go just jump on HDFS just because. But if you already have a Hadoop cluster and you want to also work with Solr, I think it's a pretty nice advantage. But the more interesting integration points and features that we worked on start now. The first one was MapReduce index building. So this is, if you have a ton of data, you got some terabytes of data, loading that into a Solr cloud cluster now can take a long time. You're basically reading the data from HDFS and you send it into your cluster, and a typical Solr cloud cluster these days isn't going to be more than a dozen nodes probably, and so you're only going to be able to load that data as fast as a dozen nodes can index. So it might take you months. Who knows? It depends on how much data you have. So this is the part that builds on, like I said, Andre's patch that he first started, and so we basically took that as our starting point and added tons of testing, tons of features, tons of options, and basically created what we call a MapReduce index building tool, which is a command line tool which will submit this job to your Hadoop cluster and basically have all of the mappers in your cluster extract the data from HDFS using Tika and other mechanisms that I'll talk about later, if it's rich text or reading from Avro files or sequence files. And it will do the extraction. It'll serialize the documents in the Java bin format, send it to reducers. Reducers will each have an embedded Solr instance that can write an index. So each reducer that you have is writing an index. This is the diagram of that. So the mappers are parsing the input and serializing it and sending it to the reducers. And then there's an arbitrary set of reducer steps where you are merging the indexes that are created down to fewer and fewer shards, because in the end you need as many shards as you have shards in your Solr cloud cluster. So it's probably going to be common that your Solr cloud cluster is going to be much smaller than your MapReduce cluster. You might have 20 Solr cloud nodes, but you might have 5,000 nodes in your MapReduce cluster, depending on who you are, or 400 nodes. And so what this lets you do is take advantage of all those 400 nodes for indexing power, and then merge all of those indexes you've built in multiple steps down to 20 shards, or however many your Solr cloud cluster can take, and then deploy them to that cluster. So it's very scalable. The first version we made, you could only use as many reducers as final shards. But then we enhanced it over time so that you could actually, create as many shards as you have reducers, and then merge them down to the final output. It's pretty scalable. There's kind of the slowest part of it is as you're merging indexes, it still does a copy, and so that's kind of currently where the main bottleneck is. But over time, we actually want to add a merge command that lets you do more of a move than a copy, and that'll kind of make that a constant time operation and speed things up even more. But even as is, this is a really scalable way to take a lot of data and plug it into your Solr cloud cluster. There's another option that we're probably going to add over time that will let you simply send from the mappers the Solr documents via Solr to a cluster kind of live, which is a way a lot of people are doing things now, but it's not quite as scalable. It's just kind of a nice option to have because that way you can actually search the data as the MapReduce job is sending it in rather than just getting it all at the end. So this tool that we made is actually fully Solr Cloud aware. You can use it without Solr Cloud and pass it various options that get it to work with a standard Solr cluster that's not Solr Cloud enabled. But if you are Solr Cloud enabled, one of the options you can pass it is the Zookeeper address. And so Solr Cloud stores the entire cluster state in Zookeeper. And so this tool is able to talk to Zookeeper and learn, okay, how many shards do you have? What are the URLs for all that shards? And then call this HTTP merge command that Solr has to merge the final indexes that it creates into your Solr cluster without you having to like move anything around. And so this is where having your index in HDFS actually has some benefits, right? So the first version of this, because Solr wasn't running on HDFS, once you actually created the indexes, you had to copy them to the local file system on each node. You couldn't just simply use them once they're in HDFS. You have to copy them out and then use them. Now, because Solr can run on HDFS, once you create them, you can simply merge them into the Solr cluster, or you can just start your Solr cluster on the outputted indexes in place. Usually you'd want to actually merge them in because that merge actually copies the data. And by copying the data, even though it's HDFS to HDFS, you'll actually get a local copy on each of your Solr nodes, which will really speed things up. So the other nice thing about HDFS, Solr on HDFS, is this merge command actually normally doesn't work that way. Normally, Solr has this merge command now, but you can only merge indexes that are on the local file system. You can't say like, merge this index on machine X to machine Y. You have to copy that index over locally and then merge it. But because we're running on HDFS and that whole merge command works with the directory abstraction, all of a sudden you can merge from anywhere because you simply give it the HDFS address of where the index you want to merge is into that Solr cluster, and it simply reads it from whatever remote place it's at without kind of any extra copying code, or it's all just kind of automatic. So now instead of having to like copy index files in and out of HDFS and figure out where things need to go, everything just kind of works just by giving it the right HDFS addresses, which is kind of nice. And so this whole merge step where once the indexes are done, you can merge it into a live cluster is a feature we call Go Live. And so basically the first iteration we did, once you created your indexes, you had to do all these manual copy steps to get the indexes into the place that you wanted. And then you'd start up your Solr Cloud cluster after setting it up to look for those indexes in the right place. And it's not that hard, but it's kind of annoying and has all these manual steps. This Go Live feature basically just lets you say, here's my Zookeeper ensemble address. You figure out everything else to get the index into the cluster. And you can then incrementally keep adding more data. Let's say you MapReduce, build a ton of indexes, and you merge it into your cluster and you're serving it. And then over the next month, you get in a ton more data, and you say, okay, now I want to add all this new data. You just run the job again, and you go live and merge all that new data into the live cluster that's already serving the old data, and you can incrementally keep adding data live on the spot. You can't currently update the same data. It's all got to be new IDs and new data. There's more work we need to do before you can actually merge in data that actually does updates. The current merge command, basically the way merge works now is it just brings in the new index and just adds those segments to the existing segments. So it doesn't really handle updates. But if you're incrementally adding data, it works pretty well. So that's basically scalable batch indexing that works really well. It's really heavily tested. It's something I'm working on contributing now. All the HDFS Solr integration is fully contributed. That is actually, I'm working on the issue that Andre started, and I've got my latest work up there. I've almost got it contributed. There's a few more little hitches that I'm working through, but hopefully that's going to be in like, let's say Solr 4.7. 4.6 is going to probably come out in a week or two, so it's not likely to make that, but probably in 4.7 we'll have that. So that gives you batch index building. The next thing we wanted to support is a near real-time option. And so for Cloudera, what they support for this type of thing, like when log data is coming in or Twitter data, is what's called Apache Flume. And so Apache Flume is a distributed, reliable, and available service for efficiently collecting, aggregating, and moving large amounts of log data and or other data, usually basically NRT data. So it does things like, when it's, if Solr can't accept, or whatever the output source is, can't accept data as fast as it's coming in, it will buffer that data in a queue. If the data gets rejected for some intermittent reason, it'll do retries for you. So it's basically a nice messaging queue service, and gives you a lot of fault-tolerant options. And so to integrate this with Solr, we contributed to the Apache Flume project what's the Flume Solr sync. Flume has these pluggable points, one of them being the sync, which is where the data goes to. And so we wrote a first-class Solr sync. There's been a couple other people who have wrote syncs for Solr and Elasticsearch and other search engines that are okay, but kind of more like one-offs. But we really worked hard with the Apache Flume team to make sure that ours was an extremely robust, really nice solution, and it got committed fairly fast. And this lets you do nice things like, you can atomically write the output to Solr and HDFS, and Flume will handle keeping that stuff in sync. Like, you won't end up with some data in HDFS that didn't make it into Solr. It's really smart about doing retries and making sure that everything that ends up in one ends up in the other. And so if you have log data coming in constantly, it's going to go through Flume, and Flume is going to send it into your live Solr cloud cluster. And if you have near real-time search turned on in your Solr cloud cluster, you're going to be able to see that data constantly as it's coming in. And we test this a lot with the Twitter fire hose, where Twitter data is constantly coming in, and this is how we do our demos, and you can just keep searching and seeing the latest stuff. This also is fully Solr Cloud aware. You pass it the Zookeeper address, basically, and then it knows which URLs to use. It uses the Cloud Solr server, SolrJ client, which is a fault-tolerant client for adding data. It knows all about your cluster. If it's adding data and a node goes down, it knows what to retry, what other nodes are up, and where to retry. It knows, just like the MapReduce indexing stuff, it can pull down the schema so that you don't have to pass your schema file around to all of these components. They all know how to read that out of Zookeeper so that they're writing your indexes in the same schema that your Solr Cloud cluster is serving the data from. So it makes configuration very simple, basically. You don't really have to tell the MapReduce or the Flume stuff anything but the Zookeeper address and the collection that you want to work with. And then everything just works. So that's the near real-time aspect, the batch aspect. The next integration point we wanted to do was HBASE. And so HBASE is basically Apache's big table, your distributed hash map, basically. And so we actually decided to do a collaboration with NG Data on this one. They make an open source project called Lily that already has some really nice HBASE integrations, so we considered them to be the experts on this type of thing. And rather than starting from the ground floor, we actually started a new open source project with them that's hosted on GitHub that basically sets this up. This is actually what I know the least about because I worked on it the least. A couple other guys on the team kind of spearheaded this. But basically, HBASE has this, this replication option, this asynchronous replication where you can replicate between data centers or whatever, kind of different than its standard region failover stuff. And so basically how this integration works is there's a component that pretends that it's another HBASE instance that's receiving these replication events. But really, it's just a component that accepts that data, and rather than being an HBASE instance, it's actually just taking that data and sending it to the Solr Cloud cluster. So it's kind of masquerading as a replication point and getting all the replication events and sending that into Solr Cloud. So it's not necessarily like once your data is in HBASE, it's guaranteed to be searchable right away. There is a slight lag. But for most use cases, it works pretty well, I think. Here's a little diagram of how that works. I got to speed up. I'm running out of time, so I'll blow through morph So one of the issues that we had while working on this was, so okay, maybe you're building indexes with MapReduce, maybe you're adding data with Flume, but one of the common things you have to do is actually extract the data from whatever input documents you have. Maybe they're Word documents, PDFs, Avro files, sequence files. Now you've got to write something or implement something to extract it. Solr has something that can work with most of these things called the Solr cell contrib, or the extraction module. It's kind of got both names. But it actually runs in process with Solr, which is not really great. If you've ever used PDF Box, sometimes you give it the wrong PDF. It's probably improved lately, but there was a time you give it the wrong PDF, and all of a sudden it uses gigabytes of memory, and you get an OOM, and your whole Solr server goes down, or it hits an infinite loop and pegs your CPU and goes down. So you really don't want to do all of this extraction inline on Solr. And in fact, it's actually really nice if you could do it in Flume or MapReduce, because those can work across tons of nodes, and you can actually split up all that extraction across many nodes rather than doing it on perhaps your loaded fewer Solr nodes that are busy serving queries and stuff. So you kind of want to do this outside of Solr, but you don't want to have to necessarily write a lot of Java code. A lot of people that use Solr are not Java programmers. They might use PHP or other things. And you don't necessarily want to have to copy, do things more than once. If you're loading data through MapReduce index building, and then later on you're adding it through Flume, you kind of want one way to ETL that data that can be reused. So another Lucene Solr committer named Wolfgang came up with this idea for morph lines, and he said, you know what, we need a configuration system that lets you just write a config file that tells you how to extract this data and then move it into Solr. And so what it can do is use Tika as well as other custom readers to read Avro sequence files, different things. Some of it uses Tika, some of it uses custom code to have this this basically ETL pipeline that gives you a config file, and then this whole pipeline can be easily embedded in other applications. So it's embedded in the MapReduce stuff, it's embedded in the Flume stuff, it's embedded in the HBASE stuff, and you can basically use this one config set to read whatever files you want and apply lots of different transformations, etc. So it's actually part of the Cloudera development kit, the CDK. It has Cloudera in the name, but it's actually nothing in it's Cloudera specific. These are just tools that anyone using Hadoop can kind of benefit from. And so that's where it is now. It's Apache 2 licensed, similar to Unix pipelines, configuration over coding, supports common Hadoop formats, Avro sequence file, but also pretty much anything that Tika supports. So basically how it works is it's basically a bunch of steps, kind of a command pattern. Each command gets a chance to process the document, or one of the first commands might be like read a line or read multiple lines, and then subsequent commands might tell it how to pull data from those lines into various fields in Solr, and subsequent commands might copy data from one field to another field and transform it as it does that. I'll show you a little example of a config file in a minute. So you can set up this whole ETL pipeline in this one config file. It's kind of I think it's called HOSCON. It's similar to a JSON format, but you can write out this whole configuration and then reuse it across all of these components, basically. There's also support for escaping out and putting a little bit of Java in that config file if you want to. Not necessarily recommended, but if there's this little two-liner that you need and you don't want to write a custom command for, you can do that. There's if-then-else conditionals. There's this try rules engine that basically lets you do hey, if this field matches this regex, do this. But if not, and it matches this regex, do this instead. But if not, and it matches this regex, do this instead. It kind of lets you do a lot of a lot of interesting things when you're trying to match log formats that might vary a little bit. That's it for that. Here's like a little example config. So say that if this is the input, this is some like common syslog input format. This is the config that will actually read it. It's got an ID, which is just the name of it. Import commands. Anything on the class path that's in these packages will be available to you. Read line will just read a line from the input file. We actually implemented a grok command. If you know like Logstash, they commonly use grok, which lets you basically have all these pre-canned regexes for common formats. We have, because those dictionary files and those regexes are all Apache licensed and open source, we just suck them in, and if you're familiar with grok, you can use this command and parse all of the same stuff. So this is the message expressions. Message is what actually reads this format. This is the example for it. And then this load Solr command is the command that knows how to actually take the result of what you just did and send it into Solr. So basically, you can then take this config file and plug it into the batch indexing, to the Flume sync, to the HBASE integration, and it will process that data in the same way without you having to duplicate any code or anything, just this one configuration file. So that's morph lines. Finally, I'm going to talk about Hue integration. Cloudera Hue is this UI project that basically gives you a UI into various Hadoop components, like an HDFS file browser. It's got stuff to help you designing pig stuff, hive stuff. And one of the new things is this Solr tab. And it's really cool. It's basically great for like rapid prototyping UIs. It's got this whole templating interface so this is templated for Twitter. You've got the little Twitter image and the username and whatever the tweet is. So we use this for a tweet demo. You've got faceting on the side. And so you can build all this with this UI. You go into this little mode and you say, hey, I want a new facet. It should be a range facet. You can tweak all these little options. You go into a templating mode and put in like image templates to get your images, and basically it lets you really rapidly with click and drag and drop design create a UI for Solr, which is really cool. And we use it a lot for demos, but a lot of people initially say they're actually not interested in using it, and then you show it to them and how quickly it is to build a UI, and people get fairly interested. So all those pieces that I've talked about so far, except for the MapReduce building, is not quite contributed. Everything else is contributed upstream, and you can use this all in Apache land. But also, we've consolidated it as part of CDH, which is Cloudera's Hadoop distribution, which is free. And so even the MapReduce stuff and all of that is fully integrated and part of what we call Cloudera Search, which you can find at that link, or just Google Cloudera Search download, and it should be like the first link. And you can get all this stuff integrated. It also comes with Cloudera Manager. If you've ever used that, that's pretty nice. It lets you deploy and monitor all of these components of a Hadoop ecosystem. And now it can also do Solr. So if you want to like deploy Solr to a 1,000-node cluster using Cloudera Manager, it makes it super simple. It's a click and drag and drop affair. And now you've got everything running and fully monitored. So we have full integration there. And I'm a little bit over on time, and that's it. Any questions? Yeah, in the back there.
I have two questions. The first one is about the batch indexing. You mentioned that you have to use the Solr embedded server. I don't know why you have to use this, because I wonder if because you have this HDFS directory, you could use the index writer directly to write into HDFS and then use the add indexes. So that's the first question. And the second question is, all this Solr integration for HDFS looks really great, but I'm just afraid of one thing, is the fact that, for example, if your name node goes down, that means that your whole cluster goes down, and not only for indexing, but also for searching. So what can be done to what could be the
So first off, so the embedded Solr, you don't have to use that. That's just kind of an implementation detail, and we have used it. Could we drop down and just use a Solr index writer instead? Sure. there actually may even be some advantages to that in that, like, currently to get the config files, we actually download them locally to a temp directory and then start the embedded Solr server off it. And if we use the Solr index writer, we could actually just, pass it in as a byte array straight. So I mean, I've thought about that. Maybe we'll do it eventually, but it's just kind of an implementation detail that I could see that happening over time. As far as the other issue, yeah, so once you rely on HDFS, you have the same issue that you rely on the name node and single point of failure, blah, blah, blah. But as far as I know, it's not a single point of failure in most distributions anymore. The various Cloudera, or not Cloudera, Hadoop vendors have, I think, solved it slightly differently, but I think even upstream Hadoop now has name node redundancy, and I don't know, we count on that to make sure the name node is up. So yeah, that's another question? Go ahead.
Hello. Yeah, my question is as well about building indexes with MapReduce. I'm using a similar approach where I use embedded Solr as well. And I do a set of iterations, like to merge the small index I build and then get the big one. But I use the MapReduce framework, but I build them in, I ask for local file system, build there the small indexes, and then upload them. And then for the iterations, I'm downloading them again, do the merges, and upload them. So now using the HDFS directory, it should be possible to actually build and merge them in HDFS directly. Right.
Yeah, and that's what we're doing. Everything is directly in HDFS.
OK. And there are no problems, for example, for optimizing or wherever, like with the HDFS directory, it works all right, like merge, optimizing, and everything.
Yeah. It's an optional step in our tool, but you can optimize as the last step. And generally, everything is very performant. I mean, as long as you have a fast enough network, HDFS has, in our experience, not been the bottleneck.
All right, thank you.
I was curious about the trade-offs of just using a single Solr against HDFS cluster versus Solr Cloud with an HDFS cluster. It seems like you could get some of the benefits maybe if your query load isn't massive and you just want to put Solr in front of HDFS if that's a valid thing that people are doing.
I don't know if people are doing it or not, but it is, I mean, in upstream Solr, it's something that will be supported, at least in the near term. With Cloudera Search, we're pretty much only supporting using HDFS and running in Solr Cloud mode, just to kind of minimize what we have to support. But upstream, every configuration is still valid. And yeah, I mean, I can see that being an option. I don't know how good it is. The real nice thing about using Solr Cloud is that you don't, everything can be learned from Zookeeper. You don't have to configure things. Failover is going to be a lot easier. That mode that's similar to HBASE, where it's going to assign indexes to other nodes when things go down, that's a lot harder to do if you don't have Zookeeper to talk to about like what nodes are available and what nodes are up. But you should be able to use non-Solr Cloud mode on HDFS, and yeah, you'll have HDFS data replication, so you're not going to lose your index. But of course, if that node goes down, until you get it back up, you're not going to be serving. Any other questions? All right, thanks a lot.